Edit tonight. We are going to spend a little time with astronomy. There is no need to remember every name, number, or distance. You can simply let the words pass by, like faint stars moving across a quiet sky. We will begin close to home, with the Earth and the Moon. Then we will drift outward through the solar system toward the Sun, the stars, and the wider galaxy. You may fall asleep at any point. The universe will continue turning without our attention, just as it has done for billions of years. Astronomy begins with a simple experience. We look upward. During the day, the sky appears blue. At night, it becomes dark enough for distant points of light to appear. Some of those points are stars. Some are planets. A few may be satellites moving silently around the Earth. The blue color of the daytime sky is produced by sunlight passing through the atmosphere. Sunlight contains many colors. When it enters the atmosphere, it encounters tiny molecules of nitrogen and oxygen. Shorter wavelengths of visible light are scattered more strongly than longer wavelengths. Blue light is scattered across the sky, reaching our eyes from many directions. The sky is not a solid blue surface. It is a view through a thin layer of gas. Compared with the size of the Earth, the atmosphere is remarkably shallow. Most of its mass lies within a few tens of kilometers of the surface. Yet this narrow layer moderates temperature, carries clouds, moves water, and protects living organisms from much harmful radiation. Above the atmosphere, the sky does not become blue. It becomes black. An astronaut in sunlight can see the bright sun against a black background, because there is almost no surrounding air to scatter the sunlight. The Earth itself is constantly moving. It rotates once in approximately 24 hours. This rotation creates the familiar cycle of day and night. The Earth rotates from west to east. Because of this, the sun appears to rise in the east and set in the west. The stars make the same apparent journey. They are not circling the Earth each day. The Earth is turning beneath them. At the equator, a point on the surface travels at more than 1,600 kilometers per hour. Due to this rotation, we do not feel the motion because it is smooth and because the atmosphere, the oceans, and nearly everything around us are moving with the planet. The Earth also travels around the Sun. One complete orbit takes about 365¼ days. This is the origin of the year. The extra fraction of a day is why calendars sometimes include a leap day. The Earth's average orbital speed is close to 30 kilometers per second. During the time it takes to hear a single calm sentence, the planet has traveled hundreds of kilometers along its orbit. Again, the movement is not normally felt. There is no sudden acceleration. There is only a steady fall around the Sun. An orbit can be understood as continuous falling. The Sun's gravity pulls the Earth inward. At the same time, the Earth has enough sideways motion to keep missing the Sun. It falls toward the Sun but never reaches it. Instead, its path curves into an orbit. The Earth's orbit is not a perfect circle. It is a slightly stretched shape called an ellipse. However, it is very close to circular. The changing seasons are not caused mainly by changes in the Earth's distance from the Sun. They are caused by the tilt of the Earth's axis. The axis is tilted by about 23½ degrees relative to the plane of the orbit. As the Earth travels around the Sun, each hemisphere spends part of the year tilted toward the Sun and part tilted away from it. When the northern hemisphere is tilted toward the Sun, sunlight arrives more directly and the days are longer there. This produces northern summer. At the same time, the southern hemisphere is tilted away. Its sunlight is less direct and its days are shorter. It experiences winter. 6 months later, the situation is reversed. The tilt also changes the path of the Sun across the sky. In summer, the Sun climbs higher. In winter, it stays lower. Near the equator, the change in daylight through the year is relatively small. Near the poles, the change becomes extreme. There can be months of continuous daylight, followed by months when the Sun never rises above the horizon. The Earth has one natural satellite, The moon is about 384,000 kilometers away on average. Light takes a little more than 1 second to travel from the moon to the Earth. The moon is smaller than the Earth. Its diameter is a little more than 1/4 of the Earth's diameter. Its gravity is about 1/6 as strong as the gravity at the Earth's surface. A person standing on the moon would still have the same mass, but would weigh much less. The moon does not produce its own visible light. It reflects sunlight. Its phases occur because we see different portions of its sunlit half as it moves around the Earth. At new moon, the moon is positioned roughly between the Earth and the sun. Its illuminated side faces mostly away from us. As it continues in its orbit, a thin crescent becomes visible. The lit portion grows through the first quarter and the waxing gibbous phase. At full moon, the Earth is positioned roughly between the sun and the moon. We see almost the entire sunlit side. Then the illuminated portion gradually decreases again. The moon takes about 27 days to orbit the Earth relative to the distant stars, but the cycle from one new moon to the next takes about 29½ days. The difference exists because the Earth is also moving around the sun. The moon must travel a little farther to return to the same position relative to the sun and Earth. The moon rotates once during each orbit. Because its rotation period and orbital period match, the same side usually faces the Earth. This is called synchronous rotation. The far side of the moon is not permanently dark. It receives sunlight just as the near side does. It is simply the side that normally faces away from Earth. The moon's surface preserves ancient history. There is almost no atmosphere to create wind or rain. Liquid water does not flow across the surface. Geological activity is limited compared with Earth. As a result, impact craters can remain visible for billions of years. The darker regions visible from Earth are broad plains of cooled volcanic rock. Early astronomers called them maria, the Latin word for seas. They are not seas. They were formed when lava filled large impact basins long ago. The lighter areas are older highlands, heavily marked by craters. Footprints left by astronauts can remain for an extremely long time. They may slowly be disturbed by tiny meteorite impacts and radiation, but there is no ordinary weather to erase them. The moon also influences the oceans. Its gravity pulls more strongly on the side of the Earth closest to it and slightly less strongly on the far side. This difference contributes to two broad tidal bulges. As the Earth rotates through these bulges, many coastlines experience rising and falling sea levels. The sun also contributes to tides. When the sun, Earth, and moon are aligned, their effects combine to produce stronger spring tides. When the sun and moon are at roughly right angles as seen from Earth, the tides are generally weaker. The moon is slowly moving away from the Earth. Measurements using lasers reflected from mirrors placed on the lunar surface show that the average distance increases by about 4 centimeters per year. At the same time, the Earth's rotation is gradually slowing. The change is extremely small on a human scale. Long ago, days on Earth were shorter and the moon was closer. Now let us drift farther outward into the wider solar system. The sun is the central object of this system. It contains more than 99% of the total mass of the solar system. The planets, moons, asteroids, comets, and smaller bodies together make up only a small remainder. The sun is a star. It appears larger and brighter than other stars because it is much closer. The next nearest star system is more than 4 light years away. The sun is about 8 light minutes away. This means sunlight reaching the Earth left the sun roughly 8 minutes earlier. When we see the sun, we see it as it was a few minutes in the past. The same is true of everything in astronomy. Light takes time to travel. Looking into space is always a form of looking backward in time. The sun's diameter is about 1,400,000 kilometers. More than 100 Earths could be placed side by side across it. Its volume could contain roughly 1 million Earths, although the sun is far less dense than the solid and liquid material of our planet. The sun is made mostly of hydrogen and helium. In its central region, pressure and temperature are high enough for nuclear fusion. Hydrogen nuclei eventually combine to form helium. A small amount of mass is converted into energy. That energy begins a slow journey outward. Inside the dense inner layers, particles of light are absorbed and re-emitted many times. The journey from the center toward the visible surface may take thousands or even hundreds of thousands of years. Once the energy leaves the sun's surface as light, it crosses the distance to Earth in only about 8 minutes. The visible surface is called the photosphere. Its temperature is close to 5,500 degrees Celsius. The center is much hotter, reaching about 15 million degrees Celsius. Above the photosphere are thinner layers of solar atmosphere. The outermost region, called the corona, extends millions of kilometers into space. Strangely, the corona is far hotter than the visible surface. Its temperature can reach more than 1 million degrees Celsius. The detailed mechanisms heating the corona are still being studied. Magnetic fields and waves in the solar plasma appear to play important roles. The sun is not a quiet, solid ball. It is a moving sphere of plasma. Its material flows, rises, sinks, and rotates. Because the sun is not solid, different regions rotate at different rates. Near the equator, one rotation takes about 25 days. Near the poles, it takes longer. The sun's magnetic field becomes twisted by this uneven rotation and by the movement of plasma. Dark sunspots appear where intense magnetic fields affect the flow of heat. They look dark only because they are cooler than the surrounding surface. They are still extremely hot. Solar activity rises and falls in a cycle lasting roughly 11 years. During active periods, the sun may release powerful eruptions. Solar flares emit radiation. Coronal mass ejections send large clouds of charged particles into space. When these particles reach the Earth, they can interact with the planet's magnetic field. Some particles are guided toward the polar regions, where they collide with atoms and molecules in the upper atmosphere. These collisions produce the aurora. In the north, it is called the aurora borealis. In the south, it is called the aurora australis. Oxygen can produce green and red light. Nitrogen can contribute blue, purple, and reddish colors. The aurora may appear to fold, ripple, or drift across the sky. Its motion is connected to changing magnetic and electrical conditions far above the surface. The sun is middle-aged. It formed about 4,600,000,000 years ago from a cloud of gas and dust. It is expected to continue fusing hydrogen in its core for roughly another 5 billion years. It will not remain unchanged forever. As the hydrogen in the core becomes depleted, the sun will gradually expand into a red giant. Its outer layers will extend far beyond their present size. Later, those outer layers will be released into space, forming a glowing shell of gas. The remaining core will become a white dwarf. A white dwarf is small, dense, and hot. It no longer produces energy through ordinary fusion. It slowly cools over an immense length of time. The solar system contains 8 recognized planets. Closest to the sun is Mercury. Mercury is a small, rocky world covered with craters. It has almost no substantial atmosphere to hold heat. Its surface experiences extreme temperature changes. In direct sunlight, some regions become hotter than 400 degrees Celsius. At night, temperatures can fall below -150 degrees Celsius. Mercury completes an orbit in only 88 Earth days. Its rotation is slower. One rotation relative to the distant stars takes about 59 Earth days. Because of the relationship between its rotation and orbit, a full solar day on Mercury from one noon to the next lasts about 176 Earth days. The second planet is Venus. Venus is similar to Earth in size, but its surface conditions are very different. Its atmosphere is thick and made mostly of carbon dioxide. Clouds contain droplets of sulfuric acid. The dense atmosphere traps heat through a powerful greenhouse effect. The average surface temperature is about 460 degrees Celsius. Venus is hotter than Mercury, even though Mercury is closer to the Sun. The atmospheric pressure at the surface is more than 90 times the pressure at sea level on Earth. Venus rotates very slowly. It also rotates in the opposite direction from most planets. On Venus, the sun would appear to rise in the west and set in the east, although the thick clouds would hide it from a person standing on the surface. Earth is the third planet. It is the only world currently known to support life. It has liquid water across much of its surface, an atmosphere rich in nitrogen and oxygen, and a magnetic field that helps shield the atmosphere from the solar wind. Mars is the fourth planet. Its reddish color comes mainly from iron minerals that have reacted with oxygen. In simple terms, much of the surface contains rust. Mars has a thin atmosphere made mostly of carbon dioxide. Surface pressure is less than 1% of that found at sea level on Earth. Mars is cold, dry, and dusty today, yet its surface contains valleys, channels, deltas, and minerals showing that liquid water existed there in the distant past. Some water remains frozen in polar caps and beneath the surface. Mars has the largest known volcano in the solar system. Olympus Mons rises more than 20 kilometers above the surrounding plains. It also has an enormous canyon system called Valles Marineris. This system stretches for thousands of kilometers. Mars has two small moons, Phobos and Deimos. They are irregular in shape and may resemble captured asteroids, although their exact origins are still discussed. Between Mars and Jupiter lies the asteroid belt. It is often imagined as a crowded field of tumbling rocks. In reality, the asteroids are usually separated by enormous distances. A spacecraft can pass through the belt without constantly avoiding objects. The largest body in the asteroid belt is Ceres. It is classified as a dwarf planet. Many asteroids are fragments left from the early solar system. Jupiter's gravity helped prevent much of the material in this region from combining into a full-sized planet. Beyond the asteroid belt is Jupiter. Jupiter is the largest planet. Its mass is more than twice the combined mass of all the other planets. It is made mainly of hydrogen and helium. It has no ordinary solid surface where a spacecraft could land. The visible bands are clouds moving in powerful atmospheric currents. Some bands flow in opposite directions, creating turbulence and enormous storms. The Great Red Spot is a long-lived storm larger than Earth, although its size has been decreasing over time. Jupiter rotates very quickly. A day lasts just under 10 hours. This rapid rotation makes the planet bulge slightly at the equator and flatten at the poles. Deep inside Jupiter, pressure becomes so great that hydrogen behaves in unusual ways. In one region, it may exist as metallic hydrogen, able to conduct electricity. Movement in this conducting material helps generate Jupiter's enormous magnetic field. Jupiter has many moons. The four largest were observed by Galileo Galilei in the early 17th century. They are Io, Europa, Ganymede, and Callisto. Io is the most volcanically active world known. It is repeatedly flexed by the gravity of Jupiter and neighboring moons. This flexing produces internal heat. Europa has a surface of water ice. Evidence strongly suggests that a global ocean of liquid water lies beneath it. Ganymede is the largest moon in the solar system. It is even larger than the planet Mercury. Callisto is heavily cratered and preserves a very old surface. Saturn is the next planet. It is famous for its rings, although the other giant planets also have ring systems. Saturn's rings are made mostly of particles of water ice mixed with darker rocky material and dust. Some particles are tiny, others are as large as houses or even larger. The main rings extend hundreds of thousands of kilometers across, but they are remarkably thin. In many places, their vertical thickness may be only tens of meters. The rings are divided into many bands and gaps. The gravity of Saturn's moons helps shape some of these structures. The rings may be relatively young compared with Saturn, although scientists continue to study their age and origin. Saturn is less dense than water on average. This does not mean it could realistically float in an ocean, since no ocean large enough exists, and the planet has no firm outer boundary. It is simply a comparison of average densities. Saturn also has many moons. Titan is the largest. It has a thick nitrogen-rich atmosphere and clouds that produce methane rain. Its surface contains rivers, lakes, and seas of liquid methane and ethane, far beneath Titan's frozen crust. There may also be a hidden ocean of liquid water. And Cetus is much smaller. Near its south pole, Jets of water vapor and ice particles erupt from cracks in the surface. These plumes provide evidence for a salty ocean beneath the ice. Some of the material from Enceladus contributes to one of Saturn's faint outer rings. If you are still listening, there is nothing you need to hold on to. The names can fade. The planets can simply pass in their quiet order. Beyond Saturn lies Uranus. Uranus is an ice giant. This term refers to its composition, which includes substances such as water, ammonia, and methane, in addition to hydrogen and helium. Methane in the upper atmosphere absorbs red light and helps give the planet its pale blue-green color. Uranus rotates on its side. Its axis is tilted by about 98 degrees. It may have been struck by a large object early in its history, although other explanations have also been proposed. Because of this extreme tilt, the seasons on Uranus are unusual. Each pole can spend many years facing toward the Sun, followed by many years facing away. One orbit around the Sun takes about 84 Earth years. Neptune is the 8th planet. It is another blue ice giant, farther from the Sun than Uranus. Neptune has some of the fastest winds measured in the solar system. They can reach speeds of more than 2,000 kilometers per hour. The energy driving this weather is not supplied only by sunlight. Neptune also releases more internal heat than it receives from the Sun. Its largest moon, Triton, moves around Neptune in the opposite direction from the planet's rotation. This backward orbit suggests that Triton may once have been an independent object captured by Neptune's gravity. Triton has a cold surface of frozen nitrogen and other ices. Spacecraft observations have revealed active plumes rising above its surface. Beyond Neptune is a broad region called the Kuiper Belt. It contains icy bodies left from the formation of the solar system. Pluto is one of them. Pluto was classified as the 9th planet for much of the 20th century. It is now classified as a dwarf planet. This change did not mean Pluto had physically changed. Only the system used by astronomers to organize objects had changed. Pluto has mountains made of water ice, broad plains of frozen nitrogen, and a thin atmosphere that expands when Pluto is closer to the Sun and partly freezes when it moves farther away. Its largest moon, Charon, is so large relative to Pluto that the two bodies orbit a point in space located outside Pluto itself. Even farther away, comets may emerge from the distant outer regions of the solar system. A comet is usually a mixture of ice, dust, and rocky material. When it approaches the Sun, heat causes some of its frozen substances to turn into gas. Gas and dust form a glowing cloud around the nucleus. The solar wind and sunlight push material outward, creating tails. A comet's tail does not simply trail behind it along the orbit. It points generally away from the Sun. The solid nucleus may be only a few kilometers across, while the tail can extend for millions of kilometers. Now we can leave the planets behind and move gently toward the stars. Stars are born within clouds of gas and dust. These clouds are sometimes called stellar nurseries. In colder, denser regions, gravity can pull material together. As a clump contracts, its center becomes hotter and denser. A rotating disk may form around it. Material within the disk may form around it. Material within the disk can later produce planets, moons, asteroids, and comets. The forming star is called a protostar. When the central temperature becomes high enough, hydrogen fusion begins. The star enters the long, stable phase called the main sequence. A star's mass is one of the most important factors determining its life. Small stars use their fuel slowly. They can remain stable for hundreds of billions or even trillions of years. The universe is not yet old enough for the smallest main sequence stars to have reached the ends of their lives. Massive stars use their fuel much faster. They are hotter, brighter, and much shorter-lived. Some survive for only a few million years. The colors of stars are related to their surface temperatures. Cooler stars appear red or orange. Hotter stars appear white or blue. This can feel opposite to everyday associations with color. In astronomy, blue stars are hotter than red stars. Our sun is sometimes described as a yellow star, but from space, its light appears close to white. The Earth's atmosphere can make it seem more yellow, especially when it is low in the sky. Stars appear to twinkle because their light passes through moving layers of the Earth's atmosphere. Small changes in air temperature and density bend the light in shifting directions. Planets usually twinkle less because they appear as tiny disks rather than nearly perfect points. Atmospheric changes affecting one part of the disk may be averaged with changes affecting another. The stars seen at night are at many different distances. The nearest star system beyond the Sun is Alpha Centauri. One member, Proxima Centauri, is about 4.2 light-years away. A light-year is a unit of distance, not time. It is the distance light travels in 1 year, roughly 9.5 trillion kilometers. If a star is 100 light-years away, the light reaching us tonight began its journey 100 years ago. Some visible stars may have changed since their light departed. A massive star might already have ended its life, while its older light continues crossing space toward us. Most stars spend the majority of their lives balancing two forces. Gravity pulls inward, pressure produced by hot gas, and energy from fusion pushes outward. As long as these effects remain in balance, the star stays relatively stable. When fuel conditions change in the core, the balance changes as well. A star similar to the Sun eventually expands into a red giant. Its outer layers cool as they spread outward, giving the star a reddish appearance. The core contracts while fusion continues in shells or begins using new fuels. Eventually, the star releases its outer layers. The exposed core becomes a white dwarf. A white dwarf can contain a mass comparable to that of the Sun within a volume similar to that of the Earth. A teaspoon of white dwarf material would weigh several tons under Earth gravity. More massive stars have more violent endings. After passing through several stages of fusion, a massive star may develop an iron-rich core. Fusing iron does not provide the energy needed to support the star. The core collapses rapidly. The outer layers fall inward and then are blasted outward in a supernova explosion. For a time, the exploding star can shine as brightly as an entire galaxy. Supernovae create and distribute many heavy elements. The calcium in bones, the iron in blood, and much of the oxygen around us were produced through processes connected to earlier generations of stars. The atoms were scattered into space, mixed into new clouds, and later became part of new stars, planets, and living things. The collapsed core left after a supernova may become a neutron star. A neutron star can hold more mass than the Sun within a sphere only about 20 kilometers wide. Its material is extraordinarily dense. Some neutron stars rotate rapidly and emit beams of radiation from their magnetic poles. When a beam sweeps across Earth, it can appear as a regular pulse. These objects are called pulsars. The first pulsar signals were so precise that researchers briefly considered whether they might have an artificial origin. They were soon understood to be natural signals from rotating neutron stars. If the collapsed core is massive enough, it can form a black hole. A black hole is a region where gravity has become so strong that beyond a boundary called the event horizon, nothing can return to the outside universe. Not even light can escape from within the event horizon. A black hole is not a hole in the ordinary sense. It is not an empty tunnel. It is a region of space-time shaped by concentrated mass and energy. From a safe distance, its gravity behaves like the gravity of any other object with the same mass. If the Sun could somehow be replaced by a black hole of exactly the same mass, the Earth would continue orbiting in much the same way. It would become dark and cold, but it would not be instantly pulled inward. Matter falling toward a black hole can form a rotating disk. Friction and compression heat the material to very high temperatures. These disks can release intense radiation before the material crosses the event horizon. Some black holes also produce narrow jets extending far into space. The jets are connected to magnetic fields and material around the black hole, not to matter escaping from inside the event horizon. Black holes come in different sizes. Stellar mass black holes form from massive stars. Supermassive black holes contain millions or billions of times the mass of the Sun. They are found in the centers of large galaxies. At the center of the Milky Way is a supermassive black hole called Sagittarius, a star. It has a mass of about 4 million suns. It is currently much less active than the central black holes of some other galaxies. A galaxy is a vast system of stars, gas, dust, dark matter, and other objects held together by gravity. The Milky Way contains hundreds of billions of stars, although the precise total is difficult to measure. It is a barred spiral galaxy. From above, it would show a central bar of stars and several curving arms. We cannot view it from the outside. We live within its disk. The pale band seen across a dark sky is our view through the crowded plane of the galaxy. The solar system is located tens of thousands of light years from the galactic center. It takes roughly 230 million years to complete one orbit around the Milky Way. The last time the solar system was in approximately this part of its galactic orbit, dinosaurs were only beginning to become prominent on Earth. The Milky Way is not alone. It belongs to a collection called the Local Group. The Local Group contains many galaxies. The largest members are the Andromeda Galaxy and the Milky Way. A third major member is the Triangulum Galaxy. Many smaller dwarf galaxies orbit or move among them. The Andromeda Galaxy is about 2.5 million light-years away. Under dark skies, it can be seen without a telescope as a faint, soft patch. The light reaching the eye from Andromeda began traveling before modern humans existed. Andromeda and the Milky Way are moving generally toward each other. In several billion years, they are expected to interact and eventually merge. The event will not resemble two solid objects colliding. Stars within galaxies are separated by such great distances that direct stellar collisions will remain unlikely. The shapes of the galaxies will be changed mainly by gravity. Their gas clouds may compress, leading to new star formation. Over time, the two systems will settle into a combined galaxy. Beyond the Local Group are larger structures. Galaxies gather into groups and clusters. Clusters connect through immense filaments, with broad empty regions between them. On the largest scales, this pattern is called the cosmic web. Much of a galaxy's mass appears to be in a form we cannot see directly. Astronomers call it dark matter. Dark matter does not seem to emit, absorb, or reflect ordinary light. Its presence is inferred from gravity. Stars and galaxies move faster than expected if only visible matter is considered. Galaxies and clusters also behave as though additional invisible mass is present. Gravitational lensing provides another clue. Mass bends space-time, and this bending changes the path of light. A massive galaxy or cluster can distort and magnify the light from objects behind it. By measuring this distortion, astronomers can estimate the distribution of mass, including mass that does not glow. Scientists still do not know exactly what dark matter is. Many possible particles have been proposed. Experiments continue to search for them. There is another mystery on even larger scales. The expansion of the universe is accelerating. The unknown cause of this acceleration is called dark energy. The name does not describe a fully understood substance. It is a label for an observed effect that has not yet been completely explained. Together, dark matter and dark energy appear to account for most of the contents of the universe. Ordinary matter, the kind that forms stars, planets, air, oceans, and people, makes up only a small fraction. Now let us drift back toward the beginning. The observable universe has been expanding for about 13,800,000,000 years. The Big Bang was not an explosion from one point into empty space. It describes an early state when the universe was much hotter and denser, followed by the expansion of space itself. There is no known central point of expansion within the universe. From any distant galaxy, other sufficiently distant galaxies would also appear to be moving away. A common comparison is the surface of a rising loaf of bread filled with raisins. As the dough expands, each raisin sees the others moving farther away. No raisin on the surface needs to be the center of the expansion. The real universe has three spatial dimensions, so the comparison is incomplete, but it can provide a gentle picture. In the early universe, conditions were too hot for ordinary atoms to remain stable. As expansion continued, the universe cooled. Within the first few minutes, simple atomic nuclei formed, mainly hydrogen and helium, with small amounts of lithium. For hundreds of thousands of years, matter existed as a hot plasma. Light could not travel freely because it was repeatedly scattered by charged particles. Eventually, electrons joined with nuclei to form neutral atoms. The universe became transparent. The light released during this transition still fills space today. It is stretched to microwave wavelengths as the universe expanded. This is the cosmic microwave background. It can be measured in every direction. Its temperature is only a few degrees above absolute zero. Tiny variations in this background reveal differences in density in the early universe. Those small differences later grew through gravity, eventually forming stars, galaxies, clusters, and the cosmic web. The first stars formed from simple gas. They contained almost none of the heavier elements found in later stars. Inside them, fusion produced new elements. Their death scattered those elements into space. Later generations of stars formed from enriched material. Planetary systems became possible. Rocky worlds required elements such as silicon, magnesium, iron, and oxygen. Life on Earth also depends on carbon, nitrogen, phosphorus, and many other elements that did not exist in large amounts at the very beginning. Astronomy is therefore partly the study of gradual complexity. Simple particles formed nuclei. Nuclei formed atoms. Gravity gathered atoms into stars. Stars created heavier elements. Those elements became new stars, planets, oceans, rocks, and eventually living cells capable of observing the sky. If you are still awake, you can let this final part become even quieter. The observable universe is extremely large. Because light travels at a finite speed, we can observe only regions whose light has had enough time to reach us. The distance to the edge of the observable universe is greater than 13,800,000,000 light-years. This is because space continued to expand while the light was traveling. The present distance to the most distant observable regions is roughly 46 billion light-years in every direction. This makes the observable universe about 93 billion light-years across. The entire universe may be much larger. It may even be infinite. Current observations do not provide a final answer. There may be regions so distant that their light will never reach us. As expansion accelerates, some galaxies will eventually become impossible for future observers in the Milky Way's region to see. Their light will be stretched and weakened. Over immense timescales, they will pass beyond a cosmic horizon. The night sky of the distant future may appear emptier. Star formation will also slow as galaxies use or lose their available gas. Long-lived red dwarf stars will continue shining after larger stars are gone. White dwarfs, neutron stars, and black holes will remain. On timescales far beyond ordinary imagination, even these objects may change. Black holes are predicted to lose energy slowly through a process called Hawking radiation. For a large black hole, this process is extraordinarily slow. The time required for evaporation can exceed the present age of the universe by an almost incomprehensible amount. The exact far future depends on the nature of dark energy, particle physics, and other questions that remain open. Scientists describe several possible cosmic endings. The best supported general picture at present is continued expansion and gradual cooling. Stars would fade. Visible energy would become increasingly difficult to find. The universe would approach a thin and quiet state. This possibility is sometimes called heat death. The name sounds dramatic, but the process would not be sudden. It would unfold across timescales so vast that ordinary numbers become difficult to feel. There would be no single final evening, no moment when everything stopped at once. There would only be longer spaces between events. Less new light, fewer active stars, a universe becoming gradually darker and more dilute, yet this distant future does not diminish the present sky. Tonight, photons are still crossing space. Some left the moon a little more than a second ago. Some left the sun about 8 minutes ago. Some began their journey from nearby stars years or decades ago. Others have traveled through the Milky Way for thousands of years. Light from distant galaxies has crossed millions or billions of light years before entering a telescope, a camera, or a human eye. Every clear night contains many different ages of light. The sky does not show one single present moment. It is a quiet collection of messages sent at different times. A nearby planet appears almost as it is now. A distant star appears as it was years ago. A galaxy appears as it was before human history. The cosmic microwave background shows the universe when it was only a small fraction of its current age. Astronomers gather these faint messages carefully. They use visible light, radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays. They also detect particles such as neutrinos. In recent years, they have measured gravitational waves, small ripples in space-time produced by accelerating massive objects. Different instruments reveal different parts of the same universe. Radio telescopes can study cold gas and distant pulsars. Infrared telescopes can look through dust and observe objects whose light has been stretched by cosmic expansion. X-ray observatories can detect extremely hot gas around black holes, neutron stars, and galaxy clusters. No single kind of light tells the entire story. Astronomy is built by placing many quiet measurements beside one another. A slight shift in a star's spectrum can reveal motion. A tiny dimming can reveal a planet passing in front of a star. A repeated wobble can show the pull of an unseen companion. A stretched image can reveal invisible mass. A faint microwave pattern can preserve information from the early universe. Even when objects are too distant to visit, their light carries clues. The colors show temperature and chemical composition. The brightness shows energy output and distance. The timing shows rotation, orbit, explosion, or collision. In this way, the universe does not remain completely silent. It sends information continuously. Much of it is weak. Much of it takes a long time to arrive, and much of it can be understood only through patience. The Earth continues rotating beneath the stars. The Moon continues moving along its orbit. The planets continue their wide paths around the Sun. The Sun travels through the Milky Way. The Milky Way moves among nearby galaxies, and space itself continues to expand. None of these motions requires us to stay awake. They will continue through the night, steady and unhurried. So now, the distances can soften. The names can disappear. The stars can return to being simple points of light beyond a quiet window. May the rest of your night be calm, dark, and peaceful. Good night.